You and welcome to our first WaiMasterClass hosted by Toronto Women in AI team. It's our pleasure to have you here today, and thank you very much for investing your afternoon. I also kindly ask everybody to mute so that this session is not disturbed. So thank you. So having said that, my name is Shimayali Singham. I'm a Toronto AI City lead. As you all know, Women in AI is a non-profit do tank. We are working towards a gender-inclusive AI. So our initiative is to inspire and educate the next generation of female leaders in AI and to increase the female participation and representation in AI-related fields. So today's masterclass will cover explainable AI and introduction to Shapley value. So this masterclass is designed to help build a basic understanding of how to compute and interpret Shapley values in the machine learning models. So let me introduce our instructor, Cathy Ong Ly. She is pursuing a PhD in medical biophysics at the University of Toronto in machine learning lab. She's working on developing an AI pipeline for interventional cardiovascular risk stratification. Part of this pipeline is also involved the investigation of bias. Her research interests are in deep learning, computer vision techniques, and cardiology. She's also a marketing manager for Women in AI Canada. So on her free time, she enjoys being active and networking with people. So I will be putting details about Cathy or how to contact her after this, masterclass, so you can get in touch with her. The quick agenda for this event today. So Cathy will be leading the class, and we will take up the Q&A session at the end of this one. So if you have any questions during the sessions, and if you want to reach out to her, please just put it in the chat box so that way she can able to answer your questions at the end of the session. So that being said, I'm giving it back to Cathy to take over. Yeah.
Thanks for the introduction, Shia. So I'm gonna post my GitHub link. Hopefully you guys have had time to look at that link, and there are some worksheets that we're going to be going through Google Colab. So if you guys have your Gmail accounts, you might want to log into those in advance. So just to get an idea of what everyone's level of knowledge is, if you want to put how much machine learning you know in the chat, or what kind of level, whether you're a novice, intermediate, or advanced, that'd be great to know. So starting off, so this masterclass is on explainable AI, and particularly Shapley values. And so the agenda is I'm going to talk a little bit about explainable AI, and then get into Shapley values. And we're going to have two examples. One, which is a Boston housing data taken, the data set is taken from Kaggle, and another example is a breast cancer data set, also taken from Kaggle. And these are two different examples. One of them is regression, and the breast cancer one will be a classification. And then afterwards, we'll have time for a Q&A. So looking at explainable AI and what it is, explainable AI is important for interpreting model predictions because it's important to help build trust with the models that you're using and understand why the model is making the decision it has made. And it's also important for improving the model itself. So whether you're on the developer end and you're trying to understand which features are contributing to the model output, there's value in that as well. It also supports the understanding of the process of the model. And by that, I mean with model development and such. So explainable AI overall helps to improve interpretability, and interpretability refers to human understanding the decision that the model is making. And so a more interpretable model makes a machine learning model easier to understand. And then, so the basis of this Shapley paper, you can find this paper on arXiv if you type in this titled, A Unified Approach to Interpreting Model Predictions. So this is a unified approach because it takes in other explainable AI methods and kind of unifies them into this one Shapley method, which stands for Shapley Additive Explanations. And Shapley was developed to alleviate the tension between model interpretability and accuracy. And so Shapley works by building a simple explanation model on top of pre-existing machine learning models. And Shapley values help give us a metric for evaluating the importance of each individual feature that is fed into the model. And essentially these values take into account the model error to help you figure out what the predictive features are. So the basis of Shapley is built off of game theory, and this is the classic Shapley value estimation algorithm. I'm not going to go into any of this math. There are amazing resources available on the mathematical basis of Shapley, but for the sake of time, I'm not going to dive into this. But I do want to discuss kind of how Shapley values work. So I have an example here. So Shapley values are based off of game theory, which is a science of strategy. And so the Shapley value works to come up with a solution of ways to fairly distribute the gains and costs of each player. So imagine you and two other friends go out for dinner and you want to Uber home. And for you to get home, it only costs $5, but for the other friend to get home, it costs them $15, and then for the last person to get home, it costs $30. So Shapley values would try to come up with a solution so that it can fairly distribute the cost of this total ride, which would be $30. And so you would take into account each individual subgroup, so each individual contribution, which would be $5 for you, $15 for your other friend, and then $30 for your friend that lives the furthest. And you would calculate these individual values for each subgroup. So you have if only you and friend B took a ride, if only you and friend C took a ride, if you went alone and only B and C took a ride together, and then if all three of you guys took a ride together, you would use Shapley values to determine what is the optimal cost that is fair for each of you guys to pay for this 3-person ride. And something that's great about Shapley values is that it's model agnostic. And what this means is that you can use it with any type of machine learning model. So you can use Shapley values to explain linear regressions or random forest or even like deep learning models. So that's one of the advantages of using Shapley. It also allows for explanation flexibility. So you can use graphics to explain what features are most important into the model. And there's representation flexibility because you can have explanations that use different feature representations as the model. And lastly, what's great about Shapley is that you can use global and local methods to interpret the model. So global being looking at the model overall, and local methods looking at an individual sample and why that sample has that prediction. So the first data set we're going to look at is the Boston housing data set. And this is a pretty clean data set on Kaggle. There's no missing values. And there's 14 different features in this data set. And these are the 14 different features. The label for this data set is median value of owner-occupied homes in the thousands. And I just wanted to note that this data set was collected from 1970s. So the median value for a house is very cheap compared to what we're looking at now. So yeah, just take that into consideration when interpreting this model. And then this classification data set we're going to use is the Breast Cancer Wisconsin Diagnostic data set. And this looks at 10 different features. And this data set was collected by having a fine needle aspiration cytology. So what that is like when you're screening for breast cancer, you take a fine needle, you'll aspirate or you'll pull out some cells, and then you'll look at the cell nuclei shown here. And then so from that cell nuclei, we can look at different parameters such as radius, texture, area smoothness. And for this data set, they have 10 features, but they took the mean, standard deviation, and the largest mean of the 3 largest values in each feature to determine what would be considered like the worst radius or the worst texture. So if everyone wants to pull up the worksheet for the Boston housing price worksheet, it should be linked in the GitHub link. Okay. So looking at the Boston housing data set, I'm using Google Colab, so you do have to pip install some dependencies. So we're going to install Kaggle and the Shapley package itself. And then we're going to load or import different packages. So OS is just the operating system so that we can link it to our data CSV location. And we're going to import pandas and NumPy as part of our data science toolkit, input Shapley, and we're going to use scikit-learn to import our classification, our regression model, and some other important metrics for dividing the data and evaluating our data set. So if you have everything loaded, you can follow along, or you can sit back and relax because I will post everything on the GitHub afterwards. And so the first thing we want to do is we want to read in our CSV file that contains the housing data. And also, if you don't have the data set loaded, I also created dummy data that you can just load. So if you want to run this cell, which is cell, it would be cell 13. You can load that in. Although the predictions might not make sense because it is just random data, but you can still visualize some things if you're using this dummy data. And so these are the 14 different features in this Boston housing data set. So the first thing we want to do after we load that data set is we can look at it. We can see that there are 506 samples and 14 columns for each feature. And we can do data.describe, which is a part of pandas. And you can just look at the mean, standard deviation, and break down different metrics of the data set itself. And so first, what we want to do is we want to grab the target variable. We're going to do target equals data.mdv as the median value for the home. And then we're going to look at the individual targets. So target.valueCounts is a way that you can look at the unique labels from this column. So the greatest amount of median values for a home is $50,000, which is not seen today. Okay, so then from the original data frame, we want to remove it so that we're not feeding our target label into our model. And then next, we want to split our data into training and testing by using scikit-learn train test split. I'm going to split it into a 80-20 split for training and testing. And we're going to use a random forest regressor. So if you want to learn more about the random forest regressor, you can hit this link to scikit-learn to look at the different inputs for this regression model. So we're going to initiate the regression model and then train our model on the training data, and then get the predictions on our X test, which is our test data. And then we can calculate the accuracy. And another great feature about Google Colab is that if you're unsure about anything, if you just hover over the function, it'll tell you what kind of score it's predicting. So this is the coefficient of determination, and you can read further into that by hovering over. And we can also look at other metrics for regression, which is the mean squared error and mean absolute error. And these are just the prediction and the ground truth, the prediction minus the ground truth squared for the squared error, and then the absolute is just the absolute difference between ground truth and predictions. So this is when we get into the fun part. So we're going to look at Shapley. And we need to run the shape.init.js to initiate JavaScript so that you'll load the images for Shapley. So the first thing we're going to do is we're going to grab the Shapley values. And we can do this by typing in shap.treeExplainer. And so this is a tree explainer that is used for tree-based models. So we're going to feed in the first parameter, which is the model that we specified as reg for regression. And then we can feed in the feature names, which would be our column names. And then we want to do dot shap values to grab, to grab the Shapley values. And then we can feed in our X test set. And for the column names, we're going to grab everything in the column name list up to the last feature, because the last feature is the label. We're going to load that. And then we're going to create an explainer model. So this explainer model is the model explanation. So we're just going to input our model here. And so these are important for producing these plots. So first we're going to start off by producing a summary plot. And the summary plot will tell us the top features that contribute to model predictions. So we're going to do shape.summary_plot. And then we'll feed in our shape values that we just computed in the cell. And then feed in our X test, our testing data set. Okay, so we can look at this summary plot, and we can see that the feature that contributes the most to the model predictions of housing prices is LSTAT. So if we go back and we look at what LSTAT is, that is the percentage of lower status of the population. And then next we have RM, which is the average number of rooms per dwelling. So you can see if your house is in an area where there's a lower percentage of population, or if you have a certain amount of rooms, these are things that can significantly contribute to the model's prediction. So this shows the top features overall, and CHAS, ZN, and RAD are other features that do not contribute as much to the model prediction. And you can see here. So if it's on the right side, then it has a positive contribution to the model. And if it's on the left side, it has a more negative contribution to the model. So if you have more rooms, then it would increase the price of your house, or the house price. Another thing, so this is like the global interpretability, because you can look at how the model is, you can look at how the features contribute to the model overall. And next we're going to look at force plots, and these look at the model interpretations locally. So we can look at it for each individual feature. So we're going to do shap.force_plot to get the force plot. And if we run the cell, we'll get something that looks like this. So this looks really confusing, but I'll break it down. So it's kind of cut off, but there's a base value. And what this base value means is it's the average of the model output over all the training data. So this is the value, 22.84, that would be predicted, or yeah, that would be predicted if we didn't know, wait. The base value is hidden under this number, but basically the base value refers to the value that would be predicted if we didn't know any of the other features. And so in red, we see features that push the prediction higher, so that would contribute to making the cost of the house higher. And then in blue, we have features that would push the prediction lower. And this is for the first, we should do this for test. And this is for the first testing example. So we can also do this. So this is just a single example, but we can also do this for another example. So if you wanted to pick the second or third sample based on indexing in Python, we can look at this. So this sample shows us that the crime rate contributes to pushing the housing price higher, but all these other features contribute to decreasing the price of this house. And lastly, we can look at partial dependence plots, and this shows the global relationship of the features with a predicted output. So if you do shap.dependence_plot and say the feature you want to look at is the number of rooms, and type in RM for rooms, shap values, and then feed in our testing data. And so this dependence plot shows us the marginal effect of one or two features on the predicted outcome. So the dependence plot on the right axis, this shows LSTAT, and this shows that LSTAT interacts most with RM. And so this shows that there is a positive kind of exponential trend between the number of rooms you have in your house and the price of your house. Another feature we can look at is CRIM. So we'll do CRIM for crime rate, and we'll do shape.dependence_plot again, and we can look at it for the test values. And this shows us, so the amount, so if you have an increased amount of crime rate, it lowers your housing price, crime rates in the area. So what we've gone over is how we can produce Shapley plots by looking at a summary plot that looks at the top features that contribute to how much a house is going to cost. We looked at force plots, which show us each individual sample and how we get the prediction of an individual sample and which features contribute to that one scenario. And then we looked at partial dependence plots that show us the relationship of a feature with a predicted output. And it also shows us a feature that it commonly interacts with in the model. So this is the pricing example. And then if you guys want to pull up the next data set, which is the breast cancer data set. So similarly, we're gonna load the dependencies. So install Kaggle in the Shapley package, and then we're gonna import what we need. So pandas, NumPy, Shapley, and Square. This time we're gonna import a random forest classifier because this is a classification problem. We're gonna mount our drive. And additionally, I did make dummy data for this one as well.
Cathy, just to let you know that we are seeing a different screen. So if you can switch it back to the other one. Yeah. No problem. Yeah.
Is this the right screen?
Yeah, now it's fine. Thank you.
Okay, so we're just gonna go back and load the pip install what we need from Kaggle and Shapley. We're gonna load our packages, and then we're gonna get our CSV and load that CSV with all the breast cancer data. And so as I was explaining, I did make a dummy, just random dummy data that you can also use to run this. And the choices are B and M for our label, because our labels are going to be benign, which is non-cancerous, and malignant, which is a cancerous diagnosis for breast cancer. And so we're looking at 10 different features. And for each of these 10 features, they also had the mean, standard error, and worst, which is taken by the 3 largest values for each feature. So if we load our data, we can look at the data set. There are 569 samples in 33 rows. So there is a random unnamed 32 column that we're going to drop. And then we're going to assign our target to bc.data diagnosis. So that is whether it is malignant or benign, so cancerous or non-cancerous. And then we're going to remove the diagnosis from the data frame so that our label is not in our feature data set. And again, we're going to split our data into training and testing at 80-20. Also, if you're not familiar, random state is just a way that you can have reproducible results. So you can choose to remove that or keep that. And then we're going to initiate our classifier, which is, you can also learn more about the random forest classifier at this scikit-learn link here. So I'm going to call the random forest classifier. Just set it to visibility. And then we're going to fit our data onto our training, or fit our model onto our training data, and then grab the evaluations. And then we can grab our accuracy metric. So the model is able to predict at a 96% accuracy whether a sample is cancerous or non-cancerous. So going back into the Shapley example, we're going to load the JavaScript for Shapley. And we're going to grab the feature names, which are our columns. So yeah, if we look at the feature names, those are just our column names. We have the radius, texture, mean, standard deviation, and worst, which is the mean of the top 3 largest values for each category. So grabbing our Shapley values, we are going to do shap.tree explainer once again, and then feed in our model, which we call CLF for classifier, and then pass in our feature names equals to feature names. And then grab these Shapley values by doing .shap_values and feeding in our test data set. And then we're going to create our explainer model by using shap.tree explainer because we're using a random forest here. So we're going to pass in our classifier. So looking at these summary plots again, we're going to do shap.summaryPlot _summary plot. Pass in these shap values, shap_values, and our X test. Okay, so this one is a bar plot because you can either have a diagnosis of malignant or benign, so cancerous or non-cancerous. And we can just check to make sure. So class 0 would be benign, which is non-cancerous, and then class 1 would be malignant. So you can see how area worst is the most important feature at contributing to whether the model is going to predict something as cancerous or non-cancerous. And perimeter worst, concave. So these are all the features that contribute. And so next we can look at individual samples by looking at a forest plot. So we're going to initiate by doing shap.force_plot. So we can see here, higher scores that are closer to 1 mean that the model is contributing to predicting something as benign. But because a sample could be benign or malignant, we can change the index of the Shapley values to look at right. So from this first sample, we can see that the model is contributing to predicting that it's benign over contributing to predicting that it is malignant. So this is what happens when you have a multi-class output where you have 2 classes. And so the features that are most important for making this prediction, once again, are shown in red, and the features that are not as important are shown in blue here. And something else to note is that the features that are closer to this division line are the features that had the most impact in contributing to the model prediction. So area worst and concavity worst, because these are closest to the boundary, these 2 features had higher importance in contributing to this sample being classified as benign. And so we can do this again just by looking at other samples, force underscore plot. And you can feed in any value in these empty boxes. So we can pick the 100th sample and just have a look as well. So this is showing that it is most likely not benign for this sample. And we can actually look by doing Y prediction to see what the model predict to confirm. So predicted that it was malignant, and that makes sense because it's lower on predicting whether it is benign. And we can also look at its ground truth just to be extra sure. The 100. Yes, so this sample is malignant, and we can also look at what the Shapley prediction looks like for shape.force. Right, so we can see that for this 100th sample, the Shapley values are showing that it was less, the probability of it being benign was low and probability of it being malignant was higher. And this shows the model contributions to that. And we can also look at the partial dependency plots for this data set as well. So we can look at the top feature, which is area worst. And so we can see that having a high area worst contributes to the prediction of whether it is malignant or benign. It also interacts often with concavity worst. And so we saw this for regression and a classification problem. And one of the main takeaways is so what? So we have all these important features, and how might this contribute to the workflow, perhaps, of detecting breast cancer or breast cancer diagnosis. So we can look at these features and maybe think about how collection of these area, perimeter, and concave and the radius is more important, and maybe we can help improve these kinds of methods or be more diligent when collecting these kinds of variables compared to the compactness or the smoothness. So yes, so overall we can use Shapley plots to explain our models and think about ways that we can improve the workflow in whether it's a health care setting or whether it's in business or with housing prices and real estate. And this kind of example breaks down the black box that machine learning often has, or deep learning often has, that we're not really sure what the model is doing. And this shows that these certain features are are more important to contributing what the model is outputting. So that's the end of the worksheets and the different tutorials. I'll be happy to take any questions now. This was a lot to digest, so don't worry if you don't fully comprehend. I'm open to taking any messages on LinkedIn afterwards as well if you have things that come up throughout the week.
So I think, Cathy, we have a couple of questions. So you can actually raise your hand using one of the reactions here. So I can unmute yourself. So we have one participant, Prakriti. She wants to ask a question. So please go ahead.
Hi, Shimayali and Cathy, and thank you so much for the session today. Is it okay if I also turn on my video? It doesn't allow me to right now.
Okay, so do you want to show yourself?
Yeah.
I think that's how the setup is at the moment. So.
Oh, okay. Okay,
yeah,
no worries.
That's how the Zoom is set up, right? So, but we can hear you. Yeah.
Okay, great. Yeah, thank you so much for the session. I think Shapley values and explainable AI is a very important topic right now. It's very difficult to make the stakeholders understand. So yeah, thank you so much. This was a very clear presentation, and thank you for walking through it. So I had a question around, actually, I was like wondering, so the first thing that we do in generally regression, so for example, logistic regression, we can use stat models library to actually just see which variables are significant and what's the impact on the target variable. So I just wanted to understand that how Shapley values is better than that in the scenario of regression, because we were able to see like very pretty plots and very in a clear fashion of which variables are impacting how much. But I didn't see any kind of significance. So like p-values associated to that variables. So I just wanted to understand how this technique is better than that. And definitely in classification and neural networks, it's definitely one of the ways to go about it. But I was just like wondering from the regression point of view.
Great question. I think one of the great things about Shapley is that you can use it for classification and regression problems, just like the fact that it has model flexibility and it's not limited to just specific regression problems. But you are correct, there are other feature values, other explainable AI methods that are specific to regression. So I'm not really sure right now what the power to Shapley is for specifically regression problems, but as a generality, instead of using different types of explainable models for different types of algorithms, Shapley comes in because you can use it for all different types of models. So if you're running multiple models, you can use a consistent method rather than using something specific to regression to explain a regression problem or something specific to classification, because then it makes it a little less comparable to one another. So I think the model flexibility is.
Oh yeah. I think you discussed about being model agnostic. Yeah, that's a great point. Thank you.
Thank you, Prakriti. And we have a couple of questions, and one from the chat and one from things. So let's just take it from the chat. So Yvonne is asking how you use Shapley values to explain your model results to management. So how it is usually received. Do you use Shapley to explain bias in the models?
Right. So in terms of explaining the model results to management, you could show them, for instance, if you had the housing price example, you could see that, the number of rooms is most important for predicting the price. So you could show that maybe to management that having increased amount of rooms gives you more space to increase the pricing of the house. So that's one of the ways that you could do it with respect to our data set that I showed, and does using Shapley explain bias in model. I would say it does explain where where the model prediction is coming from, but bias comes from a multitude of things, such as, there's data set bias, there's racial bias, there's other bias or contributing factors that contribute to bias. So I think this does add to breaking down bias within machine learning models, but you would have to have Shapley along with other things in order to fully explain what bias is.
Thank you, Cathy. And we have another question from Leslie. So I'm going to unmute you and you can ask the question.
Thank you, Shannon. My question was similar to Yvonne about regarding the bias and how do you use the model, the values to explain to people who is not versed on computer science. Thank you.
Sorry, that was kind of choppy. Could you repeat it again?
I think so she asked us pretty much similar questions about, how do the Shapley explain the bias in the model. I think you kind of touch on the previous, questions. So that's being said, I have another one, Shakshi. She wants to know how Shape can be used for global explainability of a model.
Okay, so looking at when we looked at the summary plot that showed us how all these different features were contributing to the model prediction and how the top features were listed at the top and those were the most important features for contributing to the model as a whole. And also looking at the partial dependence plots, we could see how one feature was contributes to the whole model as well. So partial dependence and summary plots.
Perfect, thank you. And we have another question from Aridi, and I'm going to unmute and please go ahead.
Yeah. Hi, Shia. Hi, Cathy. Thank you for a great presentation. My question is around, you said you work for computer vision and deep learning, right? Your experience around using deep learning models, explainability explained by Shapley. If you have any experience or like comparison over other explainable tools that we have for deep learning, so unstructured data.
Yes, so I haven't done Shapley on any of my deep learning models, but I can link you to the GitHub that is done by Scott Lundberg, I believe, and that was the person who created the Shapley paper, but he does have an example on his GitHub of how to use it with deep learning. So I can send that link as well.
That's awesome, thank you. And I have another one, Novina. She wants to ask a question. Okay, I think, yeah, go ahead, Novina.
Yeah, hi. Thank you, Cathy, for the wonderful presentation. I have some doubts regarding the first slides. It's about the local interpretability as well as global one. So if you're going to take local, it's going to be like the subset problems, right? Like you take on different subsets and explain the model. So how do you, precise on this?
So you want me to elaborate on the local interpretability for
Yeah.
Model? Okay, yeah. So with Shapley, you can look at one sample, and that's like local because you can look at how each feature contributes to the prediction of just that one sample. So with breast cancer, we could see that the area worst contributed to that one single sample, and it was important. But we could also see how other features might push down that probability of it being cancerous or non-cancerous. So by local, you can look at it for one individual sample rather than looking at for a whole, as the model as a whole.
Okay. So I get what you're saying. And I have another doubt, like if I'm going to introduce a drift in the data and your model is not going to really, it's that there are going to be any changes in the end. So how does this help my explainability? Because there are a lot of, you can do a data drift or concept drift in introduce that to understand how well my model is performing and how well I can interpret the data in the end. Like you can say about the dependency plots or something like that. So have you done that experimentation before in the drifts, like in the data?
I have an experiment with experimented with data drift with Shapley, but that would be an interesting thing for me to investigate as well. And I'd be happy to chat about it if we both try it.
Yeah, I'm just curious to know that. And next one is about like, since we use Shapley in a supervised setup, so in unsupervised setup, do you think, I'm just researching on explainable AI, so do you think like you can use this setup on an unsupervised way or not? Because there are no papers which are used on this actually in unsupervised learning especially.
I haven't investigated in that either, but I'm sure there's a researcher somewhere out there that is probably looking into that.
Yeah.
Yeah, so I don't have an answer for you on that one.
Yeah, it was quite out of the box. Yeah, thank you so much.
Actually, I think what we can do is like if you can post quite okay, get in touch with Cathy to learn further about it, want to investigate on it, so you can do that. Also, like you can visit the link that we have given for GitHub. Maybe in the future, if we come across any materials, we will update that folder as well. So you can actually get some of the paper that she suggested will be put it up there as well, so anybody can grab. So it will be a live document to use. So thank you for that. I think we have a couple of questions there, so we will take one from Prakiti. Yeah. So,
yeah, sorry.
Okay, so I think she is gone. I think, yeah. So that's about it. I think there's one more. Sakshi, you want to ask another question?
Yes. So firstly, thank you so much for this wonderful session. So the question which I want to ask is, usually the model which currently I am working on is basically from the insurance domain, and where of course we need to find out the features which plays a very important role in predicting the subrogation. Actually, we are doing the model named as subrogation. So does these values, like Shapley values, helps me out in figuring out like which features from my data plays an important role while predicting the target?
Yeah, so if you had a client and you're trying to figure out what their insurance rate would be like based on different incidences that they have, I feel like a Shapley explanation would be a great way to try to understand what kind of insurance rate that person would be priced at.
Okay, thank you. Yeah, I'll try it out that. Thank you.
I think that's about it. And I think one more question, I think, for you, Cathy. So they are curious about to know, is there any other similar methods to Shapley that can be used in the explainable AI?
Yeah, so other methods that Shapley was built off of, there's Lime, there's a few that I could link to as well. And you can also, for images, you could look at grad cams and saliency maps. So where areas of the images light up based off of model predictions. Although I want to highlight that while these models do help explain what the model is predicting, they're necessary but not sufficient. So as a whole, you would have to kind of combine multiple techniques to produce a well-explained model.
Okay. I think, thank you, Cathy. And I think she answered quite a lot of questions. So thank you very much for that. Like we said, the folder is shared and we will be updating with the links, so you can have a look at there. So that's about it. Even the presentation, if you like, we will put in there. So I have actually shared Cathy's LinkedIn, so please get in touch with her if you want to learn more about it and to have a discussion. So that's being said, thank you very much, Cathy, and audience as well, for your great questions and input and encouraging words. Having said that, so we have come to the end of this event. So it's a great learning lesson for all of us. And also, I would like to thank Francie Clement and our Toronto team, Nami, Cheryl, Riddhi, Maria, and Florentina for the help to put this together. So future, we will be running more of a technical masterclass as well. So we need your support. Yeah, so I would like to encourage you to, follow us on LinkedIn. So here is the LinkedIn link for you to get in touch with us for the future events, so you don't have to miss anything. So hope you had an interesting time. So this is it. I wish you all success. Okay, keep in touch by subscribing to our channel. Thank you very much and have a great day.